All right. How's it looking? Everybody can see this and hear me, hopefully? All right, awesome. All right, so I'd like to spend the next half hour or so talking about two of the newer models that we've added to BioGears. One that I think is somewhat a very interesting use case, and one also that I think fills in a gap that we've had in BioGears for a little bit. So again, two models. One's an oral transmucosal absorption model, and one is a gastrointestinal absorptional model, just standard, give somebody a pill and have it absorb in the GI type of model. So for both these models, I want to just give a brief overview, show some of the equations, some of the inputs you need, and then just show some of the initial results. So our motivation for looking at transmucosal drug administration is that it's a route that actually offers advantages over the GI for certain drugs, not all, but for some drugs, the mouth is a more favorable environment than the GI. It's less acidic, not as much enzymatic degradation. You get a more efficient entry to the circulation because you avoid first-pass metabolism in the liver, and you also have a very rich capillary area beneath the oral mucosa. And so our model substance that we're going to look at is oral transmucosal fentanyl citrate, or OTFC. This drug was approved for treatment for breakthrough cancer pain in the late 90s, and it was added as a battlefield analgesia option to the tactile combat care guidelines. And these guidelines actually recommend OTFC as being preferable to morphine in a lot of cases for treating moderate to severe pain. And it's got a similar effect on pain, but it's a shorter onset time to relief. And it also doesn't require any IV access, so it's a lot easier in the field in that respect. And so for these reasons, our prolonged field care contract, there was great interest in developing this model due to those applications. And then a GI model, this is required to do OTFC actually, because it turns out a lot of the fentanyl is swallowed. About 3/4 of the dose actually is swallowed, and then about a third of that swallowed amount is absorbed in the GI. So you actually get some secondary absorption there. Our PFC project also wanted to look at orally administered antibiotics, so another motivation for that model. And then in general, it's a preferred route for many drugs, and this fills a gap in BioGears that we've been missing. We've had intravenous, intramuscular, intraarterial, but we haven't had an oral drug model yet. So the OTFC model, what we decided to do with this model is we consider that the drug can be absorbed in two regions in the mouth, the buccal, which is the cheek region, and the sublingual area. We're looking at these two regions specifically because they're the most permeable, so you get a lot of drug absorption in those sites. And the reason we looked at two different regions as opposed to just one combined area is because that there is some difference in speed of absorption between these two regions. So you get a pretty rapid absorption in the sublingual area and a little more extended in the buccal area. And then due to their differences in capacities, the buccal area is larger. You see some drug stored there that diffuses through the membranes a little more slowly to enter circulation. So what we did is we followed the example of a couple other studies in the literature. They were about different drugs. We applied them to OTFC. So we have a generic saliva area. We assume a constant volume and a constant rate of swallowing. So that swallowed drug is removed from the saliva and passed down to our GI model. And then we split the sublingual and buccal areas into different layers. So we have 6 layers for each one. And so we essentially solve the diffusion equation across each of these layers. So we use central finite difference approximations. That cuts down a partial differential equation in space. It approximates it down to a ordinary differential equation, which is what BioGears can handle. We don't have any PDE capabilities currently. So we assume that all the drug in the saliva is in instant equilibrium with the top layer of each of those areas. And then again, it diffuses downwards towards this kind of basement layer that's called the lamina propria. And we have blood flow rates to those areas, and the rate of blood flow determines how much drug is absorbed and enters circulation. And all of these parameters in terms of the size of these areas, the thickness, the blood flow rates, these were all estimated based off of ranges reported in various sources. So tried as best as we could to really get specific with physiological estimates for these values. So ideally, we would use physicochemical relationships so that this model could be extended to any number of substances. So if we were able to say that, pKa and, log P, the distribution coefficient, that these are always correlated, that'd be great because we could use any substance and it would get applied. That's not always the case, sadly. So since this model was fentanyl specific, we did tune many of these parameters to make them substance specific. Or I should say fentanyl specific. So I do want to mention that the way I'm not going to show all the equations, so like for instance the partial differential equations, the diffusion equation is a pretty well-known equation, but in terms of how the drug dissolves in the saliva, we use the Nernst-Brunner equation that basically says that the rate of dissolving is dependent on the solubility of the drug, the size of the drug particles, and various physical constants like diffusion rate, particle radius, etc. And this, of course, assumes that our radius, or that our particle is spherical in general, and it assumes that it's constant during the dissolution process. So some assumptions there, but it gives a decent time profile. We did find some good estimates for the diffusivity through the saliva and the mucosa, and also for the partitioning between the saliva and the upper layer of the epithelium in both the buccal and sublingual regions. So we, again, try to use these relationships as much as possible to make this a generic model that could be extendable to other substances. But you'll see that on the bottom right here, there are some parameters that we had to tune to get a good fentanyl response, but we tried as much as possible to make sure these were validated values or assumptions that have been made in other places. They weren't just kind of come from nowhere. So I want to do a demonstration real fast of the OTFC model. So again, I want to show just what this looks like in BioGears. The demo is 800 micrograms of OTFC. That's the recommended dose in the Tactical Combat Casualty Care Guidelines. I have two different actions listed here just to show you that both the transmucosal action and the regular gastrointestinal absorption action that I'll show later, these basically go through the exact same action. You specify them with this substance oral dose action in BioGears. The only difference is you specify, do I want a transmucosal administration or gastrointestinal, meaning the drug is deposited directly into the stomach as if it were a solid pill. So this is the plasma profile of fentanyl following oral transmucosal administration. On the left is a longer 12-hour profile. On the right, we zoom in a little more to the first 4 hours. And so you can see that, again, we compare this to a study in the literature. You can see that we capture both the maximum concentration and the time of the maximum concentration really well. This is because of that rapid absorption through the mucosal area. It takes less than half an hour to get that drug really into circulation, which really helps with the pain relief aspect of fentanyl. You can see on the right side that we do capture a second local maximum. There's kind of a second peak there at about 2.5 hours. And that's where the GI absorption of swallowed fentanyl is coming into play. but it's a little bit delayed. So based off of the literature, it looks like that secondary absorption happens a little more quickly, more like an hour to an hour and a half. So absorption of fentanyl in our GI model is a little bit slower than expected. But in general, we capture pretty well the behavior there with the two maximums and also the delay in response. So a lot of plots here. These are not as critical. Really, we're validating against the plasma concentration mostly. That's the target metric we want to hit. But I did want to show you what the output of this model looks like as you diffuse through the layers. So these first two plots show you the dissolving process. You start off with 800 micrograms, and you gradually dissolve over the course of about half an hour. That is longer than reported. Usually, it's about 15 to 20 minutes for it to completely dissolve. So our dissolving assumptions might be a little bit off there, but that's something that we can certainly revisit. You can see that our saliva concentration, though, peaks pretty rapidly and then decreases as fentanyl both is swallowed and dissolves through the mucosal layer. And so you can see these 6 plots that follow are all the sublingual regions. So the number 1 is the top layer, working your way down those different layers until you get to the basement layer that borders the blood flow site. And so you've got a wave of diffusion going through these regions, and then eventually, again, drug in that bottom layer diffuses into the bloodstream. The second slide shows the same thing, only with this is the last layer of the sublingual. And then the next plots are the buccal regions, so the cheek. So you can see that this wave, compared to the sublingual area, the wave of diffusion here is slower. It takes a little bit longer for the drug to make its way all the way through, and that's consistent with this idea that the sublingual region is a little bit thinner, so drug diffuses more rapidly. The buccal layer, a little more capacity to store drug, a little bit thicker, and so you have a little bit slower of a diffusion process through it. That's the OTFC model. Then our gastrointestinal absorption model. This is an advanced compartment and transit model. These are plentiful in various modeling studies. So we've taken this existing skeleton of various ACAT models and embedded it into BioGears. So we assume that there are the stomach compartment, and that the small intestine is divided into a series of different compartments, each of them with different volume, surface areas, pHs. And we assume that each compartment has a solid and a dissolved portion to it. So solid enters the stomach. So when you administer an oral drug, it starts off in this solid stomach area. Whereas if you have a dissolved drug that's, for instance, like fentanyl, it's dissolving in the mouth and then being swallowed, that's going to enter in the dissolved portion of the stomach compartment. We have these transit constants that dictate how quickly the drug moves through the lumen of the small intestine. And at in each lumen compartment, there is permeation from the lumen into what's called the enterocyte layer of the small intestine. And so this is essentially diffusing through the lining into the bloodstream. And the reason why we distinguish, in particular, a separate compartment for this lining is because for some drugs, there's actually some metabolism that happens there. So even if some drug permeates from the lumen through the enterocyte layer, not all of it makes it to the bloodstream. So it's important for us to consider that in the event that it was important for certain drugs. So then drug that's in the enterocyte layer that is not metabolized, that partitions into the bloodstream. It enters the BioGears portal vein. And that portal vein then takes it to the liver compartment, where there's first pass metabolism that happens according to the clearance model that Austin talked about with our PK model, and then it enters systemic circulation. I do want to go into a little more detail about some of the equations for the GI model, just to mention how we derive these. So I split this up into the solid drug portion, the dissolved drug, and the enterocyte layer. The solid drug is pretty straightforward. There's either the influx comes from the previous compartment, unless it's the stomach, in which case there's no influx, it's just the initial mass that's deposited there by the oral drug action. And then mass exits the stomach compartment, or I should say solid drug exits whichever compartment you're in, by either dissolving, moving to the dissolved portion, or by being transmitted to the next compartment downstream according to these rate constants. Notice that we use the same form of a dissolving equation for the GI model as we did for the OTSC model. Right now, I'll mention this again later, but right now the solubility is not dependent on location. So really, if you're in the stomach, that's a much different environment than the mouth in terms of pH, the presence of bile salts, and that should really change the solubility of a drug. Still working on that part of the model, so right now it's just a constant value. We're looking to extend this model and make that a region-specific parameter. So dissolved drug, again, this there's influx from the previous compartment. If it's the stomach compartment, that influx comes from the OTSC model. It gains mass from whatever dissolves. There is efflux to the next compartment, and then there is permeation to the enterocyte layer. In this case, this F sub U is the fraction of drug that is unionized. So in general, neutral drugs diffuse easier than drugs that have a charge on them. And then the mass is the mass of drug in the enterocyte layer. In the enterocyte layer, again, your influx is this permeation term. Some drug is metabolized. This is a tune parameter depending on the drug. So we just change that value to help us get a good fit, basically. And then there finally is efflux to the portal vein. In this case, this fraction of blood, since there are 8 or 9 different enterocyte compartments, we just assume that there are 8 compartments, I should say. We just assume that each of those compartments receives 1/8 of the blood flow in the portal vein. So we assume that it's all distributed equally throughout the system. So the transit constants, the surface areas, the compartment volumes, and the enterocyte volumes, these were all obtained from other studies that use these advanced compartment and transit models. So like the OTSC model, we tried to get the substance-specific parameters as much as possible to be functions of existing physicochemical properties that are readily available in the literature. That just makes extending this model to new substances that much easier. So the fraction unionized, that depends on whether the drug is an acid or a base. We do have Zwitterion support. That is a little more difficult because it requires some very specific information regarding what are called microconstants. That's how the Zwitterion transitions not just from positive to negative, but how it transitions from its various tautomeric states between neutral with no charge or neutral with a charge distribution. There is an example of that for moxifloxacin that we have implemented in BioGears, but that's a very substance-specific type of a model. And our pH estimates, again, come from values in the literature. Substance permeability, this is a physicochemical empirical model that basically says that the permeation is a function of the log P, so the octanol water partition coefficient, the fraction unionized, the molecular weight, the hydrogen bond count of the model, and of the substance, and the polar surface area of the substance. So all of these all of these are log P, molecular weight, hydrogen bond count, polar surface area. All of those are inputs in the substance XML file. So that file that Austin showed for vasopressin, there are fields to enter these values. So the model will hopefully take those and get a good first approximation for what GI absorption looks like for any generic substance. Again, solubility, right now it's a constant value. We do plan to incorporate pH and bile salt effects in future releases. And the metabolism of a drug inside the enterocyte layer, we tune that for fentanyl to help with the plasma profile. For other substances, it's set to 0 until we can determine what it should be, if it's even necessary. There are a lot of studies that look at, with various enzymes, try and estimate that fraction of metabolism. But again, that's going to be sometimes, as the previous conversation showed, that data is difficult to find, so it ends up being more of a tuning parameter than a physicochemical input. So last thing I want to do is show our GI absorption model in action. So our model substance for our GI model is moxifloxacin. This was our model substance because when we were working on our infection and antibiotic model development, this was one of our substances that was called out in our prolonged field care contract as being of interest, something that you might see applied in the field. And so we give a fairly standard dose of 400 milligrams. And again, it's the same format as the transmucosal action. You just specify a gastrointestinal route as opposed to a transmucosal route. So these are the plasma, on the left is the plasma concentration profile for moxifloxacin. You can see that again. BioGears does a pretty good job of estimating it. We do peak a little bit early, it looks like, based off the data we found. It's possible that the peak plasma concentration is not observed until a couple hours after administration. But there is some disagreement about that. There are some other studies we looked at where the peak was earlier. So sometimes, again, depending on what you can find and what study population is used, you get some different targets to shoot for. So we felt pretty good about where this was at, given what we could find. The center and right plots, I just wanted to show the dissolving process in the stomach. You can see there's a pretty initially large change in dissolution there at the beginning that gradually slows over time. In about 20 minutes, all of your drug has dissolved in the stomach. And then again, on the next slide, this is the transport of the drug through the lumen of the small intestine. So from the compartment of the duodenum, which is right below the stomach, all the way through to the colon. You can see that we have this peak travels further along in time as the drug moves down the small intestine and into the large intestine. And eventually you get some relatively small masses, peaks at 8 grams, 2.5 grams. Because once you get that far down, most of the drug has been absorbed up to that point. So our future work that we want to do with this model is we want to, of course, expand our library of oral substances. Technically, you can administer any substance in our library orally right now. But right now, only moxifloxacin has had its oral PK validated to this degree. Actually, that's not true. Tylenol also. Tylenol is a new substance that Nathan has been working on, and he's got that validated, so that should be going in very soon to BioGears, which covers, and so beyond this substance and Tylenol, we want to find new substances that we can feasibly add to BioGears now that this option exists. We do want to revisit solubility in the GI, pH, bile salts. That's going to have a big impact on the dissolving timing of different drugs. And then we like to generalize the transmucosal model if we can, because it'd be interesting to be able to extend that model to other drugs and not just have it tuned specifically to fentanyl. So again, I want to thank the BioGears team for all the help and support on this project. I see there are a couple of questions on the chat here. Didn't mean to ignore them, so I'd get to them right here at the end.
Hey, Matt, great talk. Yeah, so there's a few good questions from Dan. Dan, if you'd like to interact with Matt, I'll unmute you. But I do see that your questions are there, so Matt can definitely address them from there. But thanks for participating.
Yeah, so on the first question about, I mean, yeah, clinical indication for moxifloxacins for infection, were you able to watch the talk on the inflammation and infection model, Dan?
I'm sorry, I missed that one.
Okay, well, I would point you to that one. So in that model, we look at, we do have a generic antibiotic pharmacodynamic model. So the output of that model is how much the antibiotic affects a bacteria growth rate. And so some of the results in that talk, we showed how we used piperacillin and tazobactam as our substances in that talk. But in that one, you can see how it drives down the amount of bacteria that's in our model, which leads to improvements in like the various outputs of that inflammation model. And a downstream effect of that is to improve something like blood pressure. I will say, though, that the amounts of bacteria in the model over time is not something that was validated. So you see the bacteria population decrease, but it's not fit to a particular study about piperacillin, tazobactam, or moxifloxacin against a specific infection, which is difficult to do because a lot of those studies where they're looking at, MIC and killing curves, they're done just in a petri dish, and so it's just the drug and the bacteria together by themselves, and so you have no idea how the presence of immune mediators are going to affect the interaction. So it's a difficult thing to validate.
I guess in the end, you as this person running the simulation or trying to run a simulation using these tools, you still got to kind of guess at it and make it for learning points. Decide, well, your moxifloxacin didn't work. It's nice to have your simulation behind it, but we're just not at the point where you can take it out of the hands of the operator, the simulation operator. It sounds like.
Yeah, I suppose so.
Because that's the goal.
I think right now it's where we're at is for most of the infection and inflammation, things like sepsis. Again, we're kind of just trying to hit here's an average, what an average person might look like if you did these actions and gave them these drugs and gave them this treatment. And the next step is, as one of our talks earlier showed, how can we introduce some variability of these models, possibly use machine learning techniques to really expand, patient variability, perhaps variability and sensitivity to antibiotics and the like, and how does that get us a more representative virtual population that you'd actually see in real life?
Yeah, I mean, the golden, and you guys, it's a hard thing to do. So I'm not throwing darts at you, but the golden, egg here is to try to put it in the hands of a medic so he can hit play, and the physiology engine just gives him the answers as to what's going to happen when the person, does what the person does, right? So it's tough. The real question is, you can you can physiologically predict the and show the concentrations of moxifloxacin decreasing over time, but you can't ultimately determine whether or not the moxifloxacin killed the bacteria sufficient enough to prevent sepsis. Yet.
Well, in our infection model, one of the inputs is because we recognize that there's a lot of there's just the number of possible bacteria and drug combinations. I mean, it's massive. I mean, are you targeting E. coli or are you targeting strep? I mean, we don't have that kind of resolution. So one of our compromises on that was when you specify an infection in BioGears, you need to input a minimum inhibitory concentration you want to be required to eliminate that bacteria. So, I mean, it's something you enter a priori, so it's not perfect, but
yeah, that's good. I didn't
at least investigate some simulations where you have different starting bacteria, MICs, then administer moxifloxacin and figure out, okay, it seems like, for these concentrations, are you successful or not because of the MIC of the bacteria?
Yep. Okay, that makes sense. Thanks.
Yeah.
All right. Thanks, Matt. It's a great talk and great questions too. This is all very challenging, and so it's really interesting. And it's always great to have buy-in and discussions from other people, and we always want to improve, and we always want to address these questions head on. And so I think it's great to have this discussion. So right now we are looking at about a 10-minute coffee break, and then we'll be discussing the user interface. So we will return in 10 minutes, and then we'll transition a little bit the discussion. So thank you for tuning in, and we'll be back on in 10 minutes. Hey, just real quick for everybody, like Dan said, if you weren't able to come to some of these talks, we will be PDFing all of the slides for these talks and pushing them up to be publicly available on our GitHub, so people will be able to download them and click through the slides. And then we're also saving the video recordings for this. We'll try to kind of dice it up into each talk and then upload all of those on YouTube or some similar platform so that everybody can just view the talks after the conference is over. Because I know that a lot of people have crazy schedules today because of the circumstances. So yeah, we'll try to provide everything for everybody. So Dan, you can go back and reference those talks, you know, tomorrow or the next day, whenever we get to actually getting them up onto YouTube. We should have these slides up onto GitHub relatively quickly. The YouTube part might take us a few days. So.